going to start with or continue with our materials in Chapter 2. Again, the Mastering Chemistry has been posted. I encourage you to go ahead and start taking a look at that as your time allows. You're going to need an hour or so to work on these problems in the next week or so. And I think the due date set was the 15th. We'll be through this material. We'll go ahead and start the next chapter. So I'm giving you that just so you'll have an opportunity to work on it. It's certainly in your advantage to do the material as we cover in class. That way it's fresh on your memory. So it's a strategy I encourage you to use. So the last thing we talked about was now we have a new idea for the atom. The plum pudding model wasn't true. We came up with a new model that gave us the nuclear model where we have a tiny nucleus, which contains most of the mass of the atom. It contains the protons and neutrons, and the electrons are orbiting out some far distance away. So here's a question pertaining to what we talked about yesterday. So we figured out that all of the positive charge is in a tiny core. We have 23. All right, 3 more. All right, we're all in. So almost everybody said it was choice D. It was Rutherford, and it was indeed Rutherford. He's the one that came up with the idea of the nuclear atom as we know of it today. Okay, so when we look at all these different atoms we have, and the way that we distinguish one atom from another was what's called the atomic number. And the atomic number represents the number of protons in the nucleus, and that's what defines each particular element. So we know the protons are all contained in the nucleus, but what makes an element, that particular element, is the number of protons. And the atomic number in the periodic table is represented with the number above the letter. For example, carbon has 6 protons, nitrogen has 7, oxygen has 8, etc. Hydrogen has 1. But it's that number of protons is what makes that element that element. You can take away the neutrons, you can vary that, you can change the number of electrons. It's the number of protons that define what an element is in the periodic table or when we encounter it in nature. So if we think of it simply, it's when we want to find out what element we're talking about or clarify what an element is, we need to look at whatever representation we have and understand how many protons are there. So if we look at the helium that's in a balloon and look at its nucleus, represented by the red balls, there are 2 protons. We go to element number 2 in the periodic table, we see that that's helium. Okay. If we go to something that's a little larger, look at the graphite that's in your pencil lead. That's basically just carbon. And if we could look at that and count the number of protons, there's 6 protons in the nucleus. Go to atomic number 6, and that's the density of carbon in the system. So, not the number of protons. Number of neutrons can vary, not the number of protons. The number of protons is the absolute identity of an element.
Is there like a carbon or?
We'll talk about that in just a minute.
Okay.
So there's various forms of carbon, but they're all carbon and have the same number of protons. Okay, what varies is the number of neutrons. But we'll be there in just a minute. So our organization of the periodic table is they vary with the different tables. Some have the element's name. So if you look in the, I think we're doing ebooks now. The old hard copy textbook used to have the front cover of the textbook had the element's name. So if you weren't familiar with names, you could see that. We have to get accustomed to the 2-letter abbreviation for the chemical signal. And in 2-letter abbreviations, the first letter is always capitalized. If there is 2 letters, it's lowercase always. And the atomic number, which is represented with the symbol Z, is the number of protons that's there. And we'll see that everything is either a 1 or 2-letter abbreviation. Sometimes the abbreviation is easy to figure out. Carbon starts with a C, that makes sense. Nitrogen starts with an N, that makes sense. Fluorine starts with a an F that makes sense. Neon starts with NE. It's the first two letters that make sense. Sometimes it's not as straightforward. So if you look at sodium, sodium, its abbreviation is capital NA. And the translation, why is it NA? It actually comes from the Latin word natrium, and that's where the word from sodium came from. And so that's the reason that sometimes you have a mismatch in the letters that we see here in the periodic table versus their scientific spellings of the name. So if we look at the elements in the periodic table, every element has a unique atomic number. No elements share the same number of protons in the nucleus, and they also have a unique chemical symbol that goes with that. And as I just told you, they're all either one or two letter abbreviations. If we look at things like helium's He, carbon C, nitrogen's N, do I expect you to memorize those? No, we're not going to waste our brain cells memorizing all the elements in the periodic tables. The thing that I'll tell you is you do need to know the common main group elements. So we'll need to know these are this 1A family here. We'll talk about that as we go further in the chapter. The 2As, and at least the top portion of these that are in yellow and green. So if I say, what is chlorine? I'll expect you to know that chlorine's, okay, by the time we finish the chapter up, that's Cl. So we'll need to know the common ones. Some of the ones, if you need to know, if I ask you something about cadmium, you need to look up what cadmium's abbreviation was. You look it up, that's no problem. You've got a textbook or access to a textbook. And so we're not going to memorize all those things, but this is going to be the tool that you're going to have available on tests, is this exact periodic table. It's going to be sticking a little higher on the wall, but you're going to be looking at the same thing. The other thing I'll encourage you to do, if you have vision issues where you can't read these numbers underneath, I can't read unless without fine print, without my readers on. Let me know, and when we take the test and stuff, I'll print a copy of it to give with you with the test. So that's not a problem. Otherwise, we're all just going to look up at the table. Okay, so this is about as easy as it gets. What determines the identity of an atom? Open for 100% here. Couple more. Last two. Last chance. All right. All right, we didn't make 100%. So it's the number of protons. I said that like 5 times. Okay. Pay attention. It's the thing I encourage you to do. So, all right. So now the next thing we look at is the other component that's in the nucleus, and that's the neutrons. So can you have variations of carbon? That was your question. The answer is yes. Those are called isotopes. So we know that all atoms of a given element have the same number of protons. However, they don't have to have the same number of neutrons. It's the number of neutrons that can vary that create different isotopes. For example, if I look at neon in the periodic table, find neon, it's right here, it's element 10. That tells me all the elements or atoms of neon have 10 protons. However, they can vary in the number of neutrons that they have. Some of the atoms have 10 neutrons, some have 11, some have 12. Now, all three are forms of neon. Okay? They just vary with the number of neutrons that they have. And because neutrons have significant mass associated with them, they have slightly different mass. Okay? So we know that a neutron weighs about what a proton was. It's the electrons, it's the little flyweight guys. Right? So if I vary the number of neutrons, it changes the mass significantly. So atoms that have the same number of protons but vary in the number of neutrons are what we call isotopes. Now, how many elements have isotopes? And the fact is almost all of them. There's only a couple examples of elements in the periodic table that don't. Chlorine is an example. fluorine exists as fluorine 19. We'll talk about what the 19 means in a moment. But there's just one form of fluorine that we find in nature. It's the form that has 9 protons and 10 neutrons, and that's the only one we find in nature. If we looked at carbon, other forms of carbon exist. Carbon exists in 3 common forms in nature. Okay, 2 of them are stable, one's radioactive, and we'll talk about that in just a moment. Okay, so what happens is the relative amounts of each isotope, going back to the neon, which one is going to be most abundant? That abundancy depends on partly the conditions when they were formed, and if we think of probably most of the elements that we understand today were formed from either fusion in a star, or they were formed in an explosion of a star from the scientific explanation that we have. But the naturally occurring elements, the ratios of the different isotopes are constant, they're fixed. Okay, now that's the stable forms. Sometimes there's an unstable form, and those ratios may change. For the stable forms, we call the percentages the natural abundance. Okay, it's the ratio or the percentages of each different form of the isotope. And we have an instrument called a mass spectrometer, and a mass spectrometry, what it actually does is it allows us to weigh individual atoms. Now, we can't see the individual atoms, but we can take those atoms and we can run it through the instrument, and it makes a mass measurement for us. I'll explain how it works in just a second. So the way that we keep all the different isotopes straight is we assign an identity to each unique isotope, and we do that by using what's called the mass number. And the mass number is simply the summation of the number of protons and the neutrons that's found in the nucleus of that given element. So A represents the mass number, the number of protons plus the number of neutrons. And sometimes the author of this textbook uses a configuration or a notation where they put the atomic number Z down at the bottom. For example, we talked about the different forms of neon. We talked about some of the neon had 10 neutrons, some had 11 neutrons, some had 12 neutrons. We know that all neon, to be neon, it has 10 protons. So the one that had 10 protons and 10 neutrons has a mass number of 20. The one that has 11 neutrons has a mass number of 21. And the one that has 12 neutrons has a mass number of 22. And all 3 of those are stable isotopes. And that their ratio that they found is constant in nature. And off the top of my head, I don't know what that ratio is. But if the ratio is 1 to 50 to 10, whatever the numbers are, it's going to be constant fixed at that ratio. Okay? Now, the authors use this other term to represent Z. And I'll tell you that rarely will I use that, this Z term, the atomic number. Why do you think it's not significant that we put the 10 there? Why does it not matter? Right, it's the same. So the fact that it's neon, Ne, I know that it's 10. So that's just redundancy. You'll never find an advanced chemistry text put it in this type of notation. So the way that always you're going to see me write elements out for the remainder of the time. If I were to write something like neon 20, I would write like that, versus neon 21, versus neon 22. The fact that it's Ne, I know it's 10. Okay, so I understand the authors are just trying to clarify it a little bit, but that's just not what we do in real representations. Okay. If we look at the other notation, which is the most common one, or another one that we use, we write the symbol for the element, and then we put a dash for the mass number on it. I don't like that. But, get my lighter. So we'll put the symbol for the element, and then the mass number with a dash. So neon 20, neon 21, neon 22. We just need to recognize that that's another way of expressing it. This is the way I do it. And that's the common way that we do it upper level chemistry courses. Okay, so here's an example of the abundances. So my numbers I made up a while ago were off. If I looked at the neon that existed in a neon sign, okay, so the neon, when neon glows, it's the red looking color that you see. The stuff that's blue is typically a different element. It's usually helium. It's inside of a sign that glows blue, but different elements emit off different colors when you apply an electric field to them. But the neon that exists in these different isotopes, the neon 20, okay, we know that all of them have 10 protons. It has 10 neutrons. Its natural abundance is about 90.5%. So that means if I picked up 100 neon atoms, about 90 of them would be neon 20. The neon 21 only occurs rarely. So only about 0.27%. And then neon 22, the one with 12 neutrons, is a little over 9%. And all the pieces have to equal the whole. So anytime I add all those pieces together, they should add up to what? Should add up to 100%. So if I add those up, it should be 100%. Now let's, if we add those numbers up, and I'm saying if it comes out exactly on this one, so we'd have a 0, carry a 2. Now this one does come up to exactly 100%. So that tells me if I had to do a calculation that it's right. The thing that I'll tell you is that because we can introduce a rounding error sometimes, if it adds up to plus or minus a few tenths of a percent of 100, that's fine. Okay, because sometimes we'll get a rounding error in our calculations, and we're going to look at some calculations that we do with these guys. Okay, so how many neutrons are in chlorine-37? Okay, this is not a in-depth problem. I'll give you 30 seconds to figure it out. Chlorine-37. Seconds. All right, we're all in. Let's see what we said. All right. We varied greatly between answers A, B, and C. The most predominant answer was B, but A and C are a little bit similar to one another. So let's talk to a neighbor and figure out what the correct answer is. Yep.
So what is having the extra
Oh, I'll write that down.
Why isn't it there?
why is it?
I literally wrote that down.
Have one that has an extra neutron, like top of it?
The only thing the chemical properties are the same, just changes mass. That's it. Yep. Yeah, so when you look at the carbon that's in your skin, which is one of the abundant elements that we have in us, the carbons, either carbon 12 or carbon 13, it doesn't matter which atoms. So whether it's proteins or whatever, it doesn't matter which it's in. So occasionally you got one that's got an extra neutron. That's it. Okay, vote again. One more.
What did we answer?
All right, there we go. Thank you. Okay, yeah, the mass number is the combination of those two. So if you wanted to find the number of neutrons, it's easier to set up this way in C, because if you do put the atomic number there, all you have to do is take those two things and subtract them. 20 neutrons. So that's the reason behind writing that. But if I were to see element 37, only thing I'm going to do is take the mass number less the atomic number. So I'd go find the atomic number for fluorine in the periodic table. I find the 17 above the Cl, subtract it, I get the 20 in them in there. Okay? Now, chlorine is an example that exists in a couple of different isotopes. There's chlorine 35 and there's chlorine 37, and they're closer to one another. Chlorine 35 is the most abundant. It's about 3 of those for every 1 of the chlorine 37s. Okay, so what happens with an ion? Oops, I don't want that bright pink. What happens with an ion when it gains or loses electrons? And atoms can, if they're neutral, we said that they have equal numbers of protons and electrons. Okay, and the two things cancel out in charge. So if it's a neutral atom, the number of electrons is equal to the atomic number, or the Z, whatever the atomic number is in that element. But in chemical reactions, it's common for atoms to either gain or lose electrons. And whenever we have a charged atom, that's what we call an ion. So when you see the term ion, just associate that with a charged atom. That's what we mean when we say the term ion. It's a charged atom in a system. So if we think about some of the common positively charged ones we have, it's something like the sodium +1. If it's a positively charged ion, we give it a special name. We call it a cation. If it's a negatively charged ion, such as the fluoride -1 charge, we give it the name anion. The key to remember is that both of these are examples of ions. It's just that when we give the specific name cation, it means they're positively charged. The name anion means the negative charge, but they're both ions in this example. So they both are ions to represent that it's a charged atom. Okay, so I missed a couple of slides. Do you have slides in your notes that I can go over here, or I'm going to place? They're in order?
Yeah.
Okay, so in my mind, I'm missing slides. Never mind. We'll get there in just a second. Okay, so the person that took the elements and when they were discovering all these different elements, and they're discovering elements by taking materials that are mixtures, they're isolating them out of nature, they're doing physical changes to separating them, and what they're trying to do is look for things that have new properties. It's a different boiling point, a different melting point. How is this metal different from the next metal? In the 1600s, we believed there were 4 elements. And then we started to do things to realize that there were different things that we could isolate. For example, there are places where you can go scrape a red powder out of the ground, and you take that red powder and heat it up, and the red powder decomposes into liquid mercury, and it gives off a gas. And they noted one of the gases that was from this, if they put a mouse inside of the gas, they used to play with cats and mice and everything else, they put a mouse inside the gas, they said it ran around vigorously. So what do you think the gas was giving off? Any idea? What would give something energy?
Heat.
Oxygen. So it was giving off oxygen gas. So mercury oxide was the powder, and they heated it up and it decomposed into liquid mercury and gave off oxygen. So they were using those types of techniques. They didn't know exactly what the elements were, but they were isolating things. And then we're doing comparisons to try to find out what's new. And they started trying to organize it. So how many different elements are there? A person that put together the organization that stuck was a Russian chemist in 1969. His name was Dmitry Mendeleev. He took the elements that were known, and he organized them into groups that had similar properties. Okay? He found that if you took the elements and you listed them out in order of increasing mass, that there became recurring properties in terms of some things seem to have a similar pattern. So like some metals would react to form a +1 cation. Some would react to form a +2. Some are reactive with acids, some are reactive with bases. And he started trying to characterize these and organize them into these patterns. So what he did was he listed them out from the lightest to the heaviest element based on the things that they knew, and they started to try to pair up things that had similar characteristics. And for example, like helium has similar characteristics to neon, which has similar characteristics to argon, right? And if I looked at other ones, things like lithium share characteristics with sodium, which shares characteristics with potassium. And the way he did is he listed the elements going from lightest to heaviest, but going down the periodic table, he listed those things with those characteristics. So lithium, sodium, potassium all have similar chemical and physical characteristics. On the far side of the periodic table, helium, neon, argon, and going down have similar physical and chemical characteristics. That's what we call the periodic law. So the good thing about that organization of the table, once I learned something about the characteristics of these things in the top row of the periodic table, it applies down to the things down below it. So I don't have to memorize the way everything behaves in the periodic table. Typically, I learn what happens with the top, and I know that there's something similar down below it. Okay, so that's the reason we use the periodic table as a tool. So the periodic law simply means that elements are arranged in a way of increasing mass and that you have recurring sets of periodic properties that occur. So he organized, there were several different ways they were trying to put the elements together and trying to figure out what shape to have some order associated with them. He organized all the elements that were known at the time into what was his version of the table, and it was actually competing with a different table in Europe and a table that had been introduced in the United States. Theirs were based on, one was based on sole chemical properties, one was based on 100% physical properties, but his organization gave us where the similar properties, both chemical and physical, fall into these vertical columns going up and down. And it became the organization of the periodic table that stuck today. This is the modern periodic table. Now, one of the problems in Mendeleev's times, in the 1780s or 1870s, there's some gaps. What happened is that we haven't discovered all the elements. In fact, we didn't discover complete finding all the elements of the periodic table until the 1930s. There were some that we just hadn't discovered yet. His wisdom allowed him to say that there should be something here, we just haven't found it yet. So what he did was predicted the existence of elements, and he left a blank spot for it in the table. So one example of that is what he called ectosilicon. So there was an element underneath silicon in his periodic table. That element's germanium, and it hadn't been discovered at that time. So he said something should be there. And he gave it a temporary name, the ectosilicon. So when it was discovered in 1886 by the German chemist, he named it germanium. So if you discovered an element and you're the first to prove it's yours, you get to come up with this name. So he named it after his home country, so after Germany. But it had the physical and chemical properties that very much matched what Mendeleev suggested it should be. So if we think about the modern periodic table, most of the elements are in order of, all the elements are in order of increasing atomic number relative rather than their relative mass. So there are a couple of examples where the mass is not in complete order. See if you can, what I mean by that. If we go left to right and then go down and start back over on the left, the atomic numbers are always increasing. 1 going up, 2 down in the bottom. See if you can find a place in the masses where the masses are not always increasing. Okay, 52 and 53. So 52 is had an average mass of 127.6. 53 iodine weighs 126.9. That's one of the examples. So most of the time it's increasing, but there are occasions where it doesn't. Now, the why behind that, we're going to talk about it a little bit later, but what happens is the lighter isotopes are the most abundant one, okay? Where with the element 52, the heavier isotopes are most abundant. It's the extra neutrons that are in element 52, and its stability with those heavier neutrons. The masses are not always in order. And recognizing that was a new organization of the periodic table.
Now, how did you know that there was something missing from here?
Well, he looked at things that had properties like in the 3A family, that like boron, aluminum, gallium, and then he looked in the 5A family, nitrogen, phosphorus, and arsenic, which are discovered. And when he started looking carbon, silicon, and tin, which is SN, there wasn't anything there in the mass. So he said, should be something there. We hadn't found it yet. Okay? So it was great insight on his part to do this. That's the modern periodic table we've been using since the 1870s. So if you go to a larger institution, scientific institution, so we went to the Smithsonian a few years back and got to go to the Natural History Museum. They have a great example of a modern periodic table where it has all the elements in their various containers except for the radioactive ones, and it shows them in the form that we find them in nature. And elements vary greatly in the form. So some are solids under atmospheric conditions, some are liquids under atmospheric conditions, and some are gases. So if you look at something like sulfur, it's a yellow solid. So sulfur can actually be mined down the ground in its elemental form. Can you guess of a place around here where sulfur might be found? Sulfur, Oklahoma. So there's actually a town not far from here where this element was mined. So bromine was actually mined. It was found as a liquid and extracted out of the ground at Bromide, Oklahoma. And Bromide was a place back in the early to late 1800s, before statehood of Oklahoma, where they were just digging all these different kind of rocks out of the ground and extracting different elements out of it. It's a geographically rich region. There's a lot of different types of rocks. Iodine, example, is a purple-looking solid. Carbon, if we think of carbon, carbon's one of the elements we're going to learn that has different types of forms. The most common form of carbon is like a lump of coal, graphite. All right. Then you have things that are other nonmetals. Silicon is kind of a rock form. Lead, of course, we're familiar with lead. It's a real soft metal. Copper is a little bit harder. Gold's a soft metal. Chromium's a very, very hard metal. It's a lot of different organizations or different forms that we find things in nature. They can be solids, liquids, or gas. Now, what this table tells you is it tells us some of the key characterizations we have and separations. We say that elements are either metals, non-metals, or they share the property between a metal and a non-metal. We call it a metalloid. Now, this the periodic table here in this textbook, they tricked me because this was the color scheme in the previous edition of the textbook, and blues represented metals. And just to mess me up, I think, they changed from the yellows to the blues. But you can still see the labeling in the table. So on this, we've got the nonmetals represented in the one nonmetal here. The rest of these guys are nonmetals. Okay, going to the metal side of it, looking at the metals represent this portion of the periodic table, as well as these guys down here. We'll talk about these series down here in a moment. But if you look at the periodic table, the numbering goes 57, 72. Okay, 57, 72. What the heck happened to 58? Well, those are actually plucked out and we put them down at the bottom. Those are called the lanthanide and actinide series. So here's number element 58 through 71, and then down below it, 90 through 103. So we're trying to keep the periodic tables big enough that you can see them from a distance, and also so it'll fit above this chalkboard. Where these should actually be stuck at is plucked right in this white space. But if I do that, the periodic table has to stretch way out. So we usually write it with those series plucked down below. Now the ones that are kind of the uniques or the difference are the ones that we call the metalloids. And the metalloids are all the elements that are on the dividing line, okay, so between metals and nonmetals. So they're the guys that are in here. Today, those are critically important elements for us today. These ones that are represented in green in this periodic table, because those are the basis of today's modern semiconductors. So all of your integrated circuits that made life grand for you are all a result of having these semiconductors or metalloid elements. Prior to the introduction of semiconductors, we came up with the first computers in the 1950s, actually the end of World War II, in the 1940s. The problem is every transistor was the size of a large light bulb. They got off heat. You were limited by the amount of heat that these transistors gave off to the number of calculations that could be done and how big of a space you could put it in. The first computer that Southeastern got in the late 1950s, it was in a room about the size of this, but it had to have a dedicated air conditioning system. Otherwise, it gave off so much heat. It was less powerful. You can't imagine an electronic device that's slow today. Okay, so they were limited by a couple of hundred transistors or 1,000 transistors. A modern PC computer, we'll go to something you've all got around you. Your cell phone. The computer processor in your cell phone has over 3 billion transistors in that 2 centimeter by 2 centimeter processor chip. The ability to make those switching transistors smaller and smaller and smaller is all the result of semiconductors and the ability to incorporate those to make smaller and smaller technology. It changed our lives as we know it. So again, we've got an organization that's metals, nonmetals, and metalloids. Know that layout in the periodic table. At the end of the year, you won't get the color-coded periodic table. So the test that you'll take at the end of the year, you need to know something about these relative positions. Now, the positions are important because the different types of metals have different types of characteristics or properties associated with them. So go to look at metals first. So those are the things that are on the left side in the middle of the periodic table. And the common properties they have is that they're good conductors of heat and electricity. They have a property called malleability, which I mentioned the other day. That means they can be pounded flat into a sheet. Ductility, we don't think about this one much today, but it means it can be drawn into a wire. But in the 1800s and 1900s, when they're discovering the elements, the ability to be able to industrialize a metal, to pull it into a wire was an important property they were interested in. The other characteristic is that they reflect light. They're shiny. Okay? They tend to lose electrons when they undergo a chemical reaction. So if an atom like sodium or strontium in this example, so strontium in the periodic table is element number 38. If it loses electrons off, is it going to form a cation or an anion? So if it loses electrons, okay, so if it loses electrons, that means it's going to have more protons, positively charges, than electrons. So if it loses electrons, that means more protons than electrons. And I'm going to represent electrons with an E and a negative mark, which means it's positively charged. It's a cation. Okay? So what happens is metals tend to react to form cations. Right? We'll find out the opposite occurs whenever we look at nonmetals. Okay, nonmetals are on the other side of the periodic table. So if we look at nonmetals, there are things that are in the upper right-hand corner of the periodic table. There are a total of 17 nonmetals. 5 of them are solids at room temperature. 1's a liquid at room temperature, that's bromine. And 11 are gases at room temperature. So helium, hydrogen, nitrogen, oxygen, neon, chlorine, argon, krypton, xenon, and radon. So we've got solids, liquids, and gases all represented with the phases that exist in nonmetals. If we go back to the metals, all the metals are solids at room temperature conditions, or room atmospheric pressure, except for one. What's the one you think that's not? So if we went back to the metal side of it, look at everything that's in the blue. It's mercury. Mercury's a liquid, but it's the only metal that's a liquid or that's not a solid under atmospheric conditions. And it's different. And it's got some unique properties associated with it.
Oh, we're talking about non-
Okay, these are the nonmetals. But I'm saying if we go back and compare where nonmetals are found in all three phases, metals are quite different. All the metals, with the exception of mercury, are solids. Okay, so metals can be found in different, or nonmetals can be found in the different types of phases. Metals are more strict. Okay, so the properties of nonmetals are basically opposite the metals when we talk about their characteristics. So they are poor conductors of heat and electricity. So if you want an insulator, you choose a nonmetal. Okay? They are non-ductile and non-malleable. So if you take and try to pound out a solid nonmetal, it shatters just like glass. Okay, they don't bend. Right? Their reaction is that they tend to gain electrons when they undergo chemical reactions. So if it gains electrons, if it started off to be electrically neutral, and it gains electrons, that means that it has more electrons than protons. So that means it's going to form an anion. It's going to have negative charge associated with it. So common examples of the ones that we use: carbon, oxygen, sulfur, bromine, iodine. Those are all examples of nonmetals. Everything that's in the yellow in this table. Now the ones in the middle are the metalloids. We call those the semiconductors or the semi-metals. Depending on your older technology, semiconductors is the more accepted term. That's the zigzag diagonal line that divides the periodic table between the metals and nonmetals. Most commonly, a periodic table would have it as a darkened line that separates those two things. And their characteristics and what makes them so unique is they're kind of metal and they're kind of non-metal. They have mixed properties associated with them. The ones that are classified as semiconductors is that their properties are intermediate and usually temperature dependent, including electrical conductivity. Pure silicon, if we look at silicon itself, element number 14, is an insulator. But you can take and put a very, very small amount of another metal in it, like arsenic, and this is what they do when they take a pure piece of silicon, and pure silicon looks like a mirror. I mean, it's shiny, but it's hard and brittle. Okay? There's a plant at Texas Instruments in Sherman that's got silicon wafer. They grow silicon, elemental silicon there, and they pull out these and they slice it up in a little disc, and from that they send it off and print computer chips on it or whatever the integrated circuits are. But the way that they put the components of the integrated circuits is they expose portions of the silicon to small amounts of things like arsenic and uranium, and that makes the silicon conductive. And the term they use is doping. They put it in there at a very, very small amount, only a few parts per million. And it changes the property, where it's not pure, it changes the property and turns it into a conductor. And the thing is that they're learning how to make these smaller and smaller and smaller today. It's changing our characteristics and the things that we can do with computer power. So there was an article on CNN last night that I looked on the web. And the article was, this guy was predicting World War III. You may look at that article. What was it about?
I only saw that.
Okay. It wasn't a prediction with his prediction. It's the guy that what's the electric car?
Tesla.
Tesla. It's the guy that's the president of Tesla. Elon Musk. He was predicting World War III would be something we need to be worried about. And his prediction's not North Korea attacking the United States. His concern is over artificial intelligence that's developing with rapid computer technology. And he talked about the 3 major countries in the world that are setting their defense systems up on artificial intelligence, so that the computer makes the decision without the input of mankind. That term for that's a concern. That how do we have a fail-safe to turn these things off? We're creating drones that can fly around unmanned, that can take out any vehicle, any person selectively, and they do it from a distance that you never even know the vehicle's there. We use those in warfare, but one of the things that different organizations, like the Drug Enforcement Agency, has their own drones that fly around. We see the cheap versions of drones flying around, and you go to any sporting event and you see things flying around everywhere taking pictures and stuff. But the fact that if an artificial intelligence, a computer, could take over control of something and say, well, the best way to eliminate this threat is to do this without a human decision or endpoint, that was that guy's concern, is that the computer technology is advancing more rapid than our ability to write code, and AI, artificial intelligence, may start to accelerate its own growth. So there's a ton of sci-fi movies about that, and we thought it was nothing but a sci-fi movie until we started developing technology to start to allow it to occur. Just things that keep you up at night. Okay, so we've got these things that have these unique properties, unique characteristics. So here's our organization of the periodic table. This is the same as the color code that's in here. Again, it's slightly different inside of your textbook. So when we take the periodic table and start dividing it up a little bit more, we have 2 organizations, and one group is called the main group elements. And their properties tend to largely be predictable based on where that element is in the periodic table. And we've got another group of elements we call transition elements, or transition metals, because they're all metals, and their properties are less predictable based on the position of the periodic table. It actually matters who's around them in nature that dictate or determine those properties. So where are these 2 groups of elements found at? So our main group elements are the ones in the 1A and the 2A family on the far left over here. They also include the 3A through the 8A family, so this far side. So these are our main group elements. The transition elements are the ones that are stuck in the middle and also at the bottom. So the transition elements are all these guys that are down in the middle. And the thing that you'll see, the notation that makes them a little bit different, they have a B on them, okay? The A's are easy. You start at the left, you go 1A, 2A, 3A through 8A, and everything goes sequential from left to right. B's, not so much, and we'll learn about those as we go into chemistry. 1B actually starts over here on this period, 2B, 3B, 4B, 5B, 6B, 7B, and you got 3 8Bs. Okay. Why the heck do you have 3 8Bs? We'll learn about those as we go forward and learn where the electrons can go. And these ones that are plugged down in the bottom, okay, they're part of the transition elements too that fit in here. So these guys, the main group elements, are very predictable. We know something about their properties or characteristics. We don't know as much about the ones, they're more variable. So we don't know. They can vary though with the ones that are in the middle in the transition. So if I wanted to pick something that would be a good insulator, which one would you choose? I want an element that's a good insulator. Again, it's based on the position in the periodic table. Two more. Last one. Okay, most of you said it was C. Okay, and C is the correct answer. So, what type of element is C? It's a non-mellow. And the things that are non-mellows, they're poor conductors. That makes them a good insulator. What do all the other ones have in common? Gold, copper, and sodium. They're all metals. So if I look at those positions in the periodic table, gold's AU, copper, Cu, and sodium's our other one, okay, Na. All of those are over here in the metals. All of those have those four characteristics. They're good conductors of heat and electricity. They're mountable, they're ductile, and they're shiny. Okay? The non-metals are the opposite of that. They're not shiny. They're poor conductors of heat and electricity. And then they're brittle instead of terms of being, can you bend them? Okay? So now we look at another organization we have that breaks the periodic table down further, and that's putting the elements into columns and rows. And we have some organization associated with that. So we develop or separate it into vertical columns that go up and down and horizontal rows that go left to right. The vertical columns are called a group or a family. And we exchange the term. Okay, so if you'll hear me say one or the other, they're just exchangeable. And the other organization is what's going left to right. The horizontal rows are called a period in the periodic table. So if I look at the organization of the periodic table, there are 18 groups. So there are 18 groups in the periodic table, and this periodic table actually has a numbering scheme that's easier to follow, where it goes 1 to 18 left to right on the different groups. So some of, we went through a transition where we couldn't figure out what to name things, and some periodic tables, if you look at an older periodic table, especially anything that was in the 1980s, 1990s, or 2000s, in those 30-year blocks, some had periodic tables had the 1A, 2A scheme, some had the group number 1 through 18, and some like this one had both, because what I want you to realize is you're going to run into both, depending on the textbook you pick up. And we just need to be able to associate that an 18 is equivalent to an 8A. Okay. Now the other thing are the periods that go left to right. There are 7 periods in the periodic table. So those 7 periods are shown on this table where they go from 1 to 7. Now 1 only has 2 elements in its period, hydrogen and helium. And then I drop down to the next period. Period 2 has 8. Period 3 has 8. Period 4 has a lot more. Period 5 has more. Period 6 has all of these, plus the 14 that are going across are the ones that just fell on the floor. And period 7 is the same. So the periods are not all the same width, is what I want to point out to you. So the groups are either numbered the 1 to 18 or the AB. The way that I'm going to teach you the most is going to be the AB configuration. The textbook authors, though, want you to know the 1 through 18 as well. So the ones that are in the main groups, they all have the letter A associated with them. They're the 1A through the 8A, or if you want to go through group numbers, they're 1 and 2, and then 13 through 18. Okay, so 1 and 2, and then 13 through 18. The transition elements are the ones that have the B associated with them, and their groups number 3 through 12 if you go with the straight numbering scheme. So they're the ones in the center of the periodic table. All right. So this is just another organization that we have. We start to name some of the groups and some of the periods. So here are some of the common naming that we have and ones that we need to learn. The alkali metals, right? This is the 1A family. So this is the ones on the far left of the periodic table. And those are elements that we use a lot in the lab. Okay, so things like hydrogen from hydrogen chloride, which you're going to use in the experiment tomorrow, that's where you're going to find that element. The next set of elements over are the alkali earth elements. Those are the 2A family. So the 2A family are the next one over. All right, then I'm going to go to the other main group ones first. So the halogens are the 7A family. That's these guys. All right, so they're next to the far right-hand side. What's on the far right-hand side are the noble gases. So the noble gases are the 8A family, far right of the periodic table. And then we start looking at the ones that we said were in the middle, were the transition elements. They're going to be all just stuck down in the center. Then we name a couple of periods in particular, the ones that we pluck out and put on the bottom. So those are the lanthanides. Okay, so the lanthanides are the top ones on the bottom, and the actinides are the ones below those. So that's the very bottom of the ones that we pluck out. A lot of the ones that are actinides and lanthanides are the ones that are radioactive. So something that's radioactive, as I told you all earlier, if you remember, it's going to be something represented by having a parentheses around with a mass. So let me get these guys out of the again. You see that, especially the ones on the very bottom period of the actinides, almost all of those have parentheses around them. That means that they're radioactive elements and their mass is changing based on the loss of radiation in the system. Okay, so what would the periodic table look like if we put the lanthanides and actinides in it? We spread out like that. Okay, so if we put these elements in the middle here, basically we got to break the periodic table between 3A, or 3B and 4B, spread it apart, stick these guys in the center, and that's what the true configuration of the periodic table is. Okay? And why do we not show it like that? Because you can't put it on one page. That's what it simply comes down to. So we pull these out and we put them down here at the bottom just to be able to merge these guys in together and to get it on a single page. That's a simple reason behind it. This is the true configuration that we have. And when we start talking about towards the end of the chapter where electrons go, these blocks and the way things are set up will actually start to make a lot more sense. Mendeleev's organization makes perfect sense with what we see with the chemical properties. All right, so one of the columns that has some unique characteristics is the 8A family. It's the noble gases. It is a group of elements that have similar properties as well. And their unique characteristic is their lack of chemical reactivity or their unreactivity. The one that we're most familiar with is helium. We use it in balloons. The reason we use it is because it has a density much less than that of air, being a very light gas. So it takes your balloon and makes it buoyant, makes it float. The other characteristic that's chemically important is that it's chemical stability that it has. Helium's never found in nature combined with any other elements. It's completely stable on its own. All right, it's just its configuration of protons and electrons allow it to be perfectly satisfied, as chemically stable as it can be. The other noble gases, things like neon, they're typically the same way. We find those in their pure forms. In fact, if you take air and start pumping air down out of the atmosphere, and you put more and more pressure on it to trap the gases out and convert the gases to liquids, you can isolate almost all the noble gases out of the air. Now, they're not there very much. They're all there in less than 0.1%, but they'll be found in that pure elemental form of just that element by itself. And that's because they're stable. And if you look at almost all the other elements in the periodic table, they've reacted either with themselves or something else. So you don't find them in their elemental form by themselves. All right, the alkali metals, that's the 1A family. They have a characteristic in that they are very reactive. In fact, they're so reactive that most of them will react with air. If you even take a marble-sized piece of sodium and you drop it into water, what happens is you'll have an instant explosion. The sodium reacts with the water. It produces a lot of heat and it produces a lot of hydrogen gas. As that gas starts to come out, as soon as the hydrogen gas gets in contact with oxygen, the heat from the reaction will cause it to explode. When sodium was more readily available, people would take sodium and throw a chunk of sodium in the water, and it would blow up like a stick of dynamite. I've heard of people that fished with sodium. You used to go to the old-timey drugstores, and you could buy elemental sodium, because people did chemistry at home. to make different things, a variety of different stuff, but you could use the metal order this stuff. Certainly today, it's not like it. It'll react with and this is sodium. Typically comes in something that looks like a stick of butter. Okay, and you cut off the length that you need with literally a butter knife, a spatula. But to keep it from reacting with there's a lot of moisture in the air. To keep it, especially in Oklahoma, this is the most moist year in terms of, if you went out and looked at the last couple of sunsets, you guys see the moon come up last night? Bright orange. Okay, so it's what we call harvest moon, but there's so much moisture in the atmosphere, the moon didn't turn white until it got way, way up in size. Same on the sunset. The sun, like at 7 o'clock, everything was turned orange. There's so much moisture in the atmosphere right now. This is an unusual year in terms of having this much moisture in the air. But we have to protect these metals from that, and the way that we do it is we take and put them typically in something like mineral. So the way that we have to store these, keep them away from water, is these things always have to be stored in a container of oil. And then we pull it out while it's still covered in the oil. Mineral oil is pretty thick and viscous. We'll cut out what we need and then quickly put it back in there. If the oil is allowed to run off, it'll start reacting with the oxygen in the air or the water in the air almost immediately. Now, as you go up the periodic table, the reactivity changes. Things like lithium are even more of a problem to deal with. And we'll talk about that reactivity as we go on. The next group, the 2A family, is called the alkali earth metals. And these, again, are common things that we have around us. They're fairly reactive, but not quite as much as the alkali metals. These are common elements that we have around us. So like the calcium that's in milk, it's important for our bones. In its elemental state, it reacts fairly vigorously with water. Typically, elemental calcium wouldn't explode. It doesn't give off that much heat, but it produces the hydrogen gas. Things like manganese, which is a common low-density structural metal that we use, strontium, barium, those are common ones that we have. Some of the things that have characteristics, like one of the problems that we have with manganese, we'll see in the lab, manganese solid will react with oxygen in the air to produce manganese oxide. I know that's not balanced, but the key thing is that it's not traditional fire like we think about it, but it's giving off a tremendous amount of heat and energy. And if you have something that's made out of pure manganese, and manganese is lighter than aluminum in terms of being an alloy, so you can machine it and you can have something like a car rim that's lighter than aluminum. Problem is, if you had a flat tire and you drove it on the road where you started getting sparks and got it hot enough, that piece of manganese would burst into flames and completely incinerate your car. They actually make car rims out of manganese in the 60s before they learned their lesson. They burnt several hundred cars up before they figured out. Some people don't know to stop when they have a flat, and they drove on a rim. They got that hot enough that it ignited. But if you we'll actually do this, take a piece of manganese ribbon and ignite it with a flame. It burns very hot and very bright. It's as bright as the sun. You can't hardly stand to look at it with your eyes. Super bright flame, gives off a tremendous amount of energy. Okay, halogens. Halogens are going to the right-hand side of the periodic table. It's the 7A family in the periodic table. So halogens have a characteristic in that they're very reactive. So whenever you put something like they're non-metals, and the way that we find them in nature is in the form of salts. So we never find chlorine in the form of chlorine gas in nature. All right, the way that we find chlorine in large amounts of it is like in sea salt. Okay, but it's reacted with an alkali metal, something in the 1A family, and that's where we get our common salts that we consume. Maybe it's whatever form that you want to. Something like sodium chloride. That's what we think of as common table salt. This is found in nature. and large amounts of it in nature. So we can get it out of sea salt. Where do you think we get most of the table salt that we consume? Anybody been to Utah? The Great Salt Lakes? Literally, there are several hundred square miles of lake beds that the water's evaporate off. It's just the salt in the seafloor. They literally scoop this stuff up, grind it, put it in your salt shaker. There's hundreds and hundreds of square miles of it. It's naturally occurring. It's a stable form for both of those elements. So sodium itself is very reactive in its elemental form. Chlorine itself is very reactive in its elemental form. Table salt makes food taste good. Okay, our taste buds like that sensation. Chlorine, if we were to isolate chlorine, it's a greenish yellow gas as we see it in nature. Bromine is a red-brown liquid. It's a little bit different. Iodide, it's a solid under atmospheric conditions, and what makes iodide unique is that iodide is one of the elements that undergoes sublimation. So sublimation means to go from a solid directly to a gas. It never melts and goes to a liquid. Okay, so if I have a container full of iodine crystals, and if I don't cap that off, that iodine will evaporate off into iodine gas directly, but it never melts into a liquid. If we use that you'll learn in organic chemistry for a variety of things. Fluorine is a pale yellow gas, very, very reactive substance. But again, those vary a lot. Okay, so I told you about a couple of different families and groups. Which one is unreactive? Some questions are a lot easier than others. Okay, a couple more. Last chance. There we go. All right. Almost everybody said it was choice D, and indeed it's the noble gases. So noble gases are the ones that are non-reactive. Halogens, very reactive. Alkali metals, reactive. Alkali earths are not as reactive as alkali metals, but they're still reactive. The noble gases are the ones that are not. Okay. So now we look at, we know that some elements can react to gain and lose electrons in chemical reactions. So if they lose electrons off, they make a cation. So what happens is they're going to tend to try to lose the number of electrons so that they form the same number of electrons or have the same number of electrons as the nearest noble gas. Okay? So if we look at nonmetals, the opposites are true. So nonmetals tend to gain electrons, and they're going to gain enough electrons to be the same as the nearest noble gas. Okay, what the heck does that mean? So what that means is, if I look at something like lithium, if I look at the nearest noble gas to lithium, so the nearest noble gas to lithium is either helium with 2 electrons, so I've got helium with 2 electrons, or I've got to go all the way across the periodic table to neon with 10. So it's not going to make sense that it's going to gain 8 electrons to be like neon. So what's going to happen is that lithium is going to lose 1 electron off. So it's going to lose 1 electron off. And when it does, it has 1 more electron than protons. So it started off with 3 protons and 3 electrons. When it loses 1 off, now the lithium has still the same 3 protons, but now it has 2 electrons. So its charge is a +1 cation. Okay, so it's a +1 cation. Main group elements are always the metals are going to try to lose electrons off so that they become like the closest noble gas around them. Sometimes they lose 1 electron, and everything in this 1A family loses 1. Everything in this 2A family loses 2. And if it's in the 3A family, it's going to lose 3 electrons off to form +1, +2, or +3. We'll see that on the slide in just a moment. Now, what happens with the nonmetals? The nonmetals are going to pick up electrons. Okay, so they're going to try to be like the nearest noble gas as well. So if I look at something like fluorine, start at the top. So fluorine's nearest noble gas is neon. So fluorine already has 9 protons, and if it's electrically neutral, it has 9 electrons associated with it. To be like neon, it needs to have 10 electrons. So what fluorine is going to do is it's going to react with something else, pick up an electron from it, and form the fluorine that has 9 protons and 10 electrons. Now I've got more electrons than protons, so it's going to be electrically negative. So it's going to form a -1 or a -1 anion. Cations are positive, anions are negative. And we have that same predictability. Everything in the 7A family forms a -1. In the 6A family, typically it's a -2. In the 5A family, it's a -3 because I need to pick up 1, 2, 3 electrons to be like neon. There's some predictability we have with these different elements. So these are the things that we just went over. The things in the 1A family will react to form a +1 cation. The things in the 2A family tend to lose 2 electrons off, form a +2. The things in the 7A family tend to gain 1, forming a -1 anion. The things in the family with oxygen, the 6A family, okay, that group of nonmetals tends to gain 2, form a -2 anion. And those are pretty predictable. Okay, so if we look at the main group elements, most of them have predictable charge associated with them, and that charge is equal to the group number. Okay, so if we think about what the group number is, it's 1A is going to form a +1, 2A forms a +2, 3A forms a +3. Right? For the nonmetals that we have, the anions, what it becomes predictable as well, here the charge is equal to the group number -8. So 7 -8 is a -1. 6 -8 is a -2. 5 -8 is a -3. So they're predictable as well. The problem we have is the unpredictability associated with the transition elements because they exist in several different forms. And I'll just give you one example with those. If we looked at the different forms of iron, Fe, iron could react to form +1, and we'll find that occasionally in nature. More commonly, you'll find iron react with something like oxygen to form +2 cation. It loses off 2 electrons. But also about as probable, you'll find some iron that reacts to form +3. And typically when you see rust, iron oxide on something, it's a mixture of these two things. It's not one or the other, it's a mixture of the two. Now, if you look at a piece of rust and you'll see rust that's really dark red sometimes, and sometimes it's a lighter tan color, lighter red associated with it, it's the variation in those two ratios, what form. And under the conditions in the lab, I can actually make, this one doesn't occur unless I force it to occur under controlled conditions, I can make it iron +4. So iron is stable in all these different forms, and we can create all of them. That's the problem. It's not just one form. It depends on what it's reacting with the different forms that are going to be created. So this summarizes the ones that are predictable that are known. So things that are in the 1A family, they always form a +1 cation. Right? Everything that's in the 2A family forms a +2. In the 3A family, aluminum always forms +3. Jumping to the far side, 7A family forms a -1. 6A family forms a -2. And nitrogen in the 5A family forms a -3. Okay, that's our stopping point. Thing I'll tell you, we've already covered half the material, well over half the material in the chapter. You can do 2/3 of the master now. So you get a chance this weekend, start working on this chapter. We'll finish it up on Tuesday. Then we'll start chapter 3. after three, we'll start going at a little slower pace. We're gonna be looking at the new time of church.